NICER's 2025 data just revealed neutron star radii cluster around 12 to 13 kilometers, forcing scientists to revise the dense matter equation of state that governs these cosmic objects. For decades, we've known these objects spin faster than helicopter blades, while packing the mass of our sun into a space the size of Manhattan. But these new radius measurements, combined with LIGO-Virgo's detection of neutron stars in the previously forbidden mass gap, have narrowed down the pressure inside neutron stars to values second only to black holes. This breakthrough constrains how matter behaves at twice nuclear density, conditions impossible to recreate in any laboratory on Earth. To understand how these extreme objects form, we must journey back to their violent origins, the stellar furnace that started it all. A massive star 8 times heavier than our sun begins this story, born from collapsing clouds of hydrogen and helium in a stellar nursery millions of years ago. This stellar giant ignites its nuclear furnace and sustains itself through hydrogen fusion for roughly 10 million years, with temperatures approaching billions of degrees as hydrogen nuclei slam together to create helium and release tremendous energy. Inside the core, thermonuclear fusion creates an outward pressure that fights against gravity's relentless pull inward. The star exists in perfect balance, with fusion energy pushing outward exactly matching gravitational force pulling inward. This equilibrium sustains the star's life, allowing it to shine brilliantly across the cosmos. But this cosmic furnace operates on borrowed time because massive stars burn through their hydrogen fuel at an alarming rate, consuming their nuclear fuel in a fraction of the time it takes smaller stars. When the hydrogen in the core finally runs out, the delicate balance that kept the star stable begins to shift. Without hydrogen fusion to provide outward pressure, gravity gains the upper hand. The core starts to contract under its own weight, and as it shrinks, the temperature rises dramatically. The compression heats the core enough to ignite helium fusion, creating carbon and oxygen in a new source of energy that temporarily restores the balance between gravity and radiation pressure. The helium burning phase marks the beginning of the star's death spiral. While hydrogen burning sustained the star for millions of years, helium fusion lasts only about 1 million years. The star has entered a period of increasingly rapid fuel consumption where each successive burning phase becomes shorter and more violent than the last. The star's outer layers begin to expand dramatically as the core undergoes these rapid changes, transforming the stellar giant into a red supergiant with a diameter that could encompass the orbit of Jupiter. The star races through its remaining fuel sources in an accelerating cascade of nuclear burning. Carbon ignites and burns for nearly 600 years, creating neon, sodium, and magnesium in increasingly complex nuclear reactions. Neon burning follows, lasting only about 1 year as neon atoms break apart and recombine to form oxygen and magnesium. Oxygen fusion creates silicon and sulfur in reactions that sustain the star for just 6 months. The core has become a layered structure, like a cosmic onion, with each shell burning a different element. Silicon burns in the innermost region, surrounded by shells of oxygen, neon, carbon, helium, and hydrogen burning in sequence. Silicon burning represents the star's last stand against gravitational collapse, creating calcium, titanium, chromium, and finally iron through a complex series of reactions that astronomers call the silicon burning cascade. This final phase lasts only days. Iron nuclei begin to accumulate in the star's core, and this marks the beginning of the end. Iron sits at the peak of nuclear binding energy, meaning it cannot be fused to release energy like lighter elements. When iron atoms fuse together, they actually absorb energy instead of releasing it. The star has reached a nuclear dead end where fusion can no longer provide the outward pressure needed to support the core against gravity. As iron accumulates, the core becomes increasingly unstable. Iron nuclei fill the center of the star like nuclear ash from millions of years of fusion burning. The temperature continues to rise, but no amount of heat can make iron fusion energetically favorable. The core grows more massive with each passing hour as silicon burning continues to produce iron in the surrounding shell. The star's core approaches the critical mass limit discovered by physicist Subramanian Chandrasekhar. When the iron core reaches approximately 1.4 solar masses, electron degeneracy pressure can no longer support it against gravitational collapse. The core has become a ticking time bomb, supported only by the quantum mechanical properties of electrons that resist being squeezed into the same energy states. Even this quantum resistance has its limits. As the iron core grows beyond the Chandrasekhar limit, the electrons and protons get crushed together with such force that they combine to form neutrons and neutrinos. This process removes the electron degeneracy pressure that was holding up the core, and gravity finally wins its million-year battle against nuclear forces. The stage is now set for one of the most violent events in the universe. The iron core has reached its breaking point, teetering on the edge of catastrophic collapse. 8 million years of stellar evolution have led to this critical moment where the fundamental forces of nature will clash in a battle that unfolds faster than human perception can follow. When giants collapse in milliseconds, the collapse happens faster than a single heartbeat. When the iron core reaches the Chandrasekhar mass limit of 1.4 solar masses, electron degeneracy pressure fails completely, and gravity wins its million-year battle in spectacular fashion. The extreme pressure forces electrons and protons together so violently that they combine to form neutrons and neutrinos in a process called neutronization. The core that once measured thousands of kilometers across shrinks to just 20 kilometers in radius within 1/100th of a second. This neutronization process releases an enormous burst of neutrinos that carry away 99% of the collapse energy. The neutrino detection from Supernova 1987A confirmed this theoretical prediction when astronomers observed billions of these ghostly particles streaming from the explosion. Most neutrinos escape the star completely, but their detection provided direct evidence of the core collapse mechanism that creates neutron stars. The core reaches nuclear density when neutrons pack together so tightly that they touch each other directly. At this point, the core contains more mass than our entire sun compressed into a sphere smaller than Manhattan. The matter becomes so dense that a cubic centimeter weighs as much as a mountain. This marks where the collapse suddenly stops because neutrons resist being compressed further due to their quantum mechanical properties. The halt in core collapse creates one of the most dramatic reversals in physics. The infalling matter racing toward the center at tremendous speeds suddenly encounters the incompressible neutron core. This collision generates a shockwave that propagates outward through the star, marking the beginning of the supernova explosion that will tear through the star's outer layers. The shockwave races outward through the star's layers, carrying more energy than our sun will produce in its entire lifetime. The explosion tears through the star's outer envelope, blasting the hydrogen-rich layers into space at speeds exceeding 10,000 kilometers per second. The expanding debris forms a shock front that plows through the surrounding interstellar medium, creating a bubble of hot gas and radiation. The energy released during the supernova explosion staggers the imagination. In the span of a few seconds, the explosion generates more energy than 1 trillion suns combined. The explosion becomes so bright that it can be seen from distances measured in billions of light years, appearing as a new star in the sky that gradually fades over weeks or months. The supernova light curve follows a predictable pattern as different radioactive elements decay in the expanding debris. The initial flash comes from the shock heating of the outer layers. Over the following weeks, the light comes primarily from the decay of radioactive nickel-56 created during the explosion. This radioactive decay powers the supernova's glow for months after the initial blast. Most importantly, the explosion enriches the surrounding space with heavy elements forged through rapid neutron capture processes during the supernova itself. Gold, platinum, uranium, and other elements heavier than iron form in the extreme conditions of the explosion through what astronomers call the R process. These elements get dispersed into space where they can eventually become incorporated into new stars and planets, seeding the universe with the building blocks of complexity. While the outer layers get blasted into space, the core survives the explosion as a neutron star. The core's incredible density allows it to withstand the violence of the supernova blast. The newborn neutron star measures only 20 kilometers across, but contains 1.4 times the mass of our Sun. The surface gravity becomes 200 billion times stronger than Earth's gravity, creating conditions unlike anywhere else in the universe. The neutron star inherits the angular momentum of the original star's core. As the core collapsed, conservation of angular momentum caused it to spin faster, much like a figure skater spinning faster when pulling in their arms. The resulting neutron star can rotate hundreds of times per second, creating a cosmic lighthouse that beams radiation across space with each rotation. The magnetic field of the original star also gets compressed along with the core. The neutron star's magnetic field becomes trillions of times stronger than Earth's magnetic field. These intense magnetic fields channel particles and radiation along magnetic field lines, creating beams of energy that sweep across space as the neutron star rotates. The neutron star's surface temperature reaches millions of degrees immediately after formation. The heat comes from the gravitational energy released during the core collapse and from the ongoing decay of radioactive elements. The surface gradually cools over thousands of years, but the interior remains hot for much longer due to the star's incredible density and thermal capacity. From the violent destruction of a massive star emerges an object that challenges our understanding of physics. The neutron star represents matter in its most extreme form, where the normal rules of chemistry and atomic structure no longer apply. These stellar remnants spin and emit radiation for billions of years, serving as cosmic laboratories for studying physics under conditions impossible to recreate on Earth. For decades, astronomers thought they understood the basic properties of these exotic objects. The theoretical models seemed solid, the mass limits appeared well established, and the physics looked settled. But the universe had other plans, and 2025 brought observations that would force scientists to completely reconsider everything they thought they knew about neutron stars. The 2025 mass mystery that changed everything. LIGO-Virgo gravitational wave detectors began recording signals that defied theoretical predictions. For decades, physicists believed neutron stars had a strict mass limit around 2.2 times the mass of our Sun. This limit came from our understanding of how matter behaves under extreme density. Beyond this threshold, gravity should overwhelm any force that could support the neutron star, causing it to collapse into a black hole. The physics seemed clear and the mathematics appeared solid. Then the detectors started finding neutron stars that should not exist. The collaboration detected gravitational waves from neutron star mergers involving objects with masses reaching 2.5 solar masses. These observations shattered our confidence in theoretical predictions about neutron star maximum masses. The detected objects clearly exhibited neutron star characteristics in their gravitational wave signatures, yet they exceeded the mass limits that our best theories said were impossible. These discoveries forced physicists to confront an uncomfortable reality about the fundamental nature of matter itself. The signal designated GW230529 provided one of the most puzzling examples of this mass mystery. The gravitational wave detection revealed the merger of two compact objects with distinctly different masses. The lighter object measured between 1.2 to 2.0 solar masses, clearly within the neutron star range. The heavier object weighed slightly more than twice the mass of our Sun, placing it in a region that astronomers call the mass gap. This mass gap represents the mysterious zone between the heaviest confirmed neutron stars and the lightest known black holes. The mass gap has perplexed astronomers for years because stellar evolution models predict that objects in this range should be extremely rare. Stars that collapse to form compact objects in this mass range should either produce lighter neutron stars or heavier black holes. The existence of objects with masses in the gap suggests that our understanding of stellar collapse and compact object formation contains significant gaps. The 2025 gravitational wave detections revealed that these gap objects might be more common than previously thought. LIGO-Virgo detected 5 or 6 additional events involving neutron stars colliding with black holes throughout 2025. These detections provided crucial data about the mass distribution of compact objects in binary systems. The neutron stars in these systems consistently showed masses near or above the previously accepted maximum limits. The pattern emerging from these detections indicated that massive neutron stars might represent a significant fraction of the neutron star population rather than rare exceptions. The implications for nuclear physics run much deeper than simple mass measurements. The equation of state describes how matter behaves under extreme pressure and density conditions found inside neutron stars. This equation determines the relationship between pressure, density, and mass for neutron star matter. The 2025 mass measurements forced physicists to reconsider fundamental assumptions about how nuclear matter behaves at densities several times that of atomic nuclei. Previous equations of state predicted that neutron star matter would become soft at high densities, meaning it would compress easily under increasing pressure. Soft equations of state naturally limit neutron star masses because the matter cannot provide sufficient pressure support against gravity. The discovery of 2.5 solar mass neutron stars requires stiffer equations of state where matter resists compression more effectively at extreme densities. The stiffening of the equation of state at high density suggests that neutron star cores might contain exotic forms of matter not found anywhere else in the universe. Normal neutron star matter consists primarily of neutrons with small fractions of protons and electrons. At higher densities, exotic particles like hyperons, kaons, or even deconfined quarks might appear. These exotic matter states could provide additional pressure support that allows neutron stars to reach higher masses before collapsing. The boundary between neutron stars and black holes has become increasingly blurred by these discoveries. Traditional models predicted a sharp transition where neutron stars above a certain mass would immediately collapse to form black holes. The 2025 observations suggest a more complex picture where some objects exist in an intermediate state. These objects might represent neutron stars on the verge of collapse or exotic compact objects that are neither traditional neutron stars nor black holes. Some theoretical models propose that the most massive neutron stars might contain quark cores where the strong nuclear force breaks down completely. In these cores, quarks would exist as free particles rather than being confined within neutrons and protons. Quark matter could potentially support higher masses than conventional neutron matter, explaining how neutron stars reach 2.5 solar masses without collapsing. The transition to quark matter might occur gradually rather than through a sharp phase transition. Rotation might play a crucial role in supporting these massive neutron stars against gravitational collapse. Rapidly spinning neutron stars experience centrifugal forces that provide additional support against gravity. The most massive neutron stars detected through gravitational waves might represent rapidly rotating objects that can maintain higher masses than non-rotating neutron stars. The rotation would gradually slow down over time, potentially leading to delayed collapse. The 2025 discoveries suggest that neutron star physics operates in regimes where multiple exotic effects become important simultaneously. The combination of rotation, magnetic fields, temperature, and exotic matter states creates a complex environment where traditional approximations break down. Understanding these massive neutron stars requires sophisticated models that account for all these effects working together. The mass mystery revealed by 2025 gravitational wave detections has opened new frontiers in both nuclear physics and astrophysics. These discoveries demonstrate that neutron stars continue to surprise us with their extreme properties. But mass represents only one aspect of these cosmic objects. The forces that shape neutron stars extend far beyond gravitational attraction, reaching into realms where the fundamental forces of nature operate at their absolute limits. Magnetic fields that bend reality. The magnetic fields surrounding these stellar remnants represent the most powerful electromagnetic forces in the known universe. Neutron stars possess magnetic fields that are 1 trillion times stronger than Earth's magnetic field. These cosmic magnets create forces so intense they can literally bend the shape of atoms and twist the very fabric of space around them. Where Earth's magnetic field measures about 50 microtesla, neutron star magnetic fields can exceed 100 million Tesla, making them the most powerful magnets in the known universe. The 2025 radio telescope observations revealed magnetic field structures that challenged everything astronomers thought they knew about these cosmic dynamos. The European Southern Observatory's upgraded radio array detected complex magnetic field geometries extending far beyond the neutron star surface. These observations showed magnetic field lines twisted into helical patterns that spiral outward for thousands of kilometers. The field structures appear to change dynamically over timescales of hours or days, suggesting active magnetic processes occurring in the neutron star's magnetosphere. Advanced radiopolarimetry measurements captured the three-dimensional architecture of these magnetic fields in unprecedented detail. The data revealed that neutron star magnetic fields are far more complex than the simple dipole fields that scientists had assumed for decades. Instead of resembling a bar magnet with two poles, these fields showed multipole components with magnetic hot spots and cold regions distributed across the neutron star's surface. Some neutron stars exhibited quadrupole or octupole field components that created intricate patterns of magnetic field lines extending into space. The most extreme examples of magnetic field strength come from magnetars, a special class of neutron stars with magnetic fields so powerful they affect the quantum vacuum of space itself. These objects generate magnetic fields exceeding 10 to the power of 15 Gauss, which is strong enough to disrupt the electromagnetic interactions between photons and virtual particle pairs that constantly appear and disappear in empty space. The vacuum polarization effect caused by these fields creates a form of magnetic birefringence where space itself becomes optically active. In 2025, the InSight HXMT team achieved the first direct measurement of a neutron star's surface magnetic field by detecting cyclotron resonance scattering features in X-ray spectra. The team discovered a cyclotron absorption line with an energy of 146 keV in the X-ray binary Swift J0243.6 plus 6 124, corresponding to a surface magnetic field strength exceeding 1.6 billion Tesla. This measurement provided concrete evidence that neutron star magnetic fields are significantly stronger than previous indirect estimates had suggested. These incredible magnetic fields serve as cosmic particle accelerators that can propel charged particles to velocities approaching the speed of light. Electrons and protons get caught in the magnetic field lines and spiral along them while gaining tremendous energy. The acceleration process occurs through magnetic reconnection events where field lines break and reconnect, releasing stored magnetic energy as kinetic energy of charged particles. These accelerated particles create the intense radiation beams that make neutron stars visible across vast distances. The magnetic field lines extend thousands of kilometers beyond the neutron star surface, creating a complex magnetosphere filled with charged particles and electromagnetic radiation. The 2025 observations revealed that these magnetospheres are not static structures, but dynamic environments where plasma flows along magnetic field lines at relativistic speeds. The interaction between the neutron star's rotation and its magnetic field creates electric fields that can accelerate particles to energies exceeding those produced by the most powerful particle accelerators on Earth. The lighthouse effect that makes pulsars visible results from the interaction between the neutron star's magnetic field and its rapid rotation. As the neutron star spins, its magnetic field sweeps through space like a cosmic lighthouse beam. The fastest spinning neutron star known, PSR J1748-2446 AD, rotates 716 times per second, making it one of the most rapidly spinning objects in the universe alongside other millisecond pulsars. Charged particles get accelerated along the magnetic field lines and emit synchrotron radiation that forms narrow beams extending from the magnetic poles. When these beams sweep across Earth's line of sight, we detect regular pulses of radio waves, X-rays, or gamma rays with precise timing. The timing precision of these pulses rivals atomic clocks, enabling astronomers to use networks of pulsars as gravitational wave detectors. The NanoGrav Collaboration's 2025 detection of the gravitational wave background used this extraordinary timing precision from pulsar timing arrays. The regular pulse arrivals from multiple pulsars across the galaxy create a cosmic timing network sensitive to the stretching and compression of space-time caused by gravitational waves from supermassive black hole mergers throughout the universe. Magnetic reconnection events observed in 2025 provided new insights into the dynamic nature of neutron star magnetospheres. These events occur when magnetic field lines with opposite orientations come together and reconnect, releasing enormous amounts of stored magnetic energy in sudden bursts. The reconnection process can heat plasma to temperatures exceeding 100 million degrees and accelerate particles to near light speeds. Radio telescopes detected these events as sudden brightening episodes followed by changes in the pulsar's pulse profile and timing. The most dramatic magnetic field reorganization events come from starquakes that literally crack the neutron star's crust and rearrange its magnetic field structure. These starquakes occur when the neutron star's rigid crust cannot adjust to changes in the star shape caused by magnetic field evolution or rotational slowdown. The crust fractures along lines of weakness, releasing energy equivalent to a magnitude 23 earthquake. The fracturing process can suddenly reconfigure the magnetic field geometry, leading to changes in the neutron star's electromagnetic emission that persist for years. Neutron star magnetic fields create some of the most efficient generators in the universe by converting rotational energy into electromagnetic radiation. The rotating magnetic field acts like a cosmic dynamo that generates electric currents flowing through the neutron star's magnetosphere. These currents create secondary magnetic fields that interact with the primary field to produce complex electromagnetic wave patterns. The power output from this magnetic generator can exceed 10 to the power of 35 watts, making neutron stars more luminous than many stars despite their small size. These magnetic phenomena demonstrate that neutron stars operate as natural laboratories for studying electromagnetic physics under conditions impossible to recreate on Earth. The combination of extreme magnetic field strength, rapid rotation, and ultra-dense matter creates an environment where quantum electrodynamics, plasma physics, and general relativity all play important roles simultaneously. Yet, for all the complexity visible in their magnetic fields and radiation patterns, the true mystery of neutron stars lies hidden beneath their surfaces, where matter exists. The hidden architecture beneath the surface. NICER's 2025 observations revealed the layered complexity that defines these cosmic objects from surface to core. The Neutron Star Interior Composition Explorer aboard the International Space Station revolutionized our knowledge of neutron star interiors through precise X-ray timing measurements. By observing how X-rays from neutron star surfaces vary as these objects rotate, NICER mapped the distribution of hotspots and determined the relationship between neutron star mass and radius. These measurements provided the first direct constraints on the equation of state of neutron star matter, revealing that these objects possess a complex internal structure with distinct layers, each governed by different physical processes. The outermost layer, known as the outer crust, consists of a crystal lattice of atomic nuclei immersed in a sea of electrons. This region extends from the surface down to depths where the density reaches about 400,000 grams per cubic centimeter. In this zone, matter behaves somewhat like terrestrial solids, but with densities millions of times greater than anything found on Earth. The nuclei in the outer crust become increasingly neutron-rich as depth increases, creating isotopes that are completely unstable under normal conditions but remain stable under the extreme pressures inside neutron stars. Deeper within the neutron star, the inner crust presents a realm where matter organizes itself into structures that physicists call nuclear pasta. These formations get their culinary names from their resemblance to various pasta shapes, but they represent some of the strongest materials in the universe. As density increases beyond the outer crust, protons and neutrons begin to arrange themselves into elongated structures called spaghetti pasta, where nuclear matter forms long, thin strands aligned in parallel configurations. The nuclear pasta phases become increasingly complex as density continues to rise. Spaghetti pasta gives way to sheet-like structures called lasagna pasta, where nuclear matter organizes into flat, parallel layers separated by regions of lower density. These lasagna structures can extend for hundreds of meters while maintaining thicknesses of only a few femtometers. The strength of nuclear pasta exceeds that of steel by a factor of billions, making it the strongest known material in the universe. At even higher densities, the pasta structures transform into three-dimensional configurations resembling gnocchi or Swiss cheese. These gnocchi pasta phases consist of spherical bubbles of low-density matter embedded in a matrix of high-density nuclear material. The transition between different pasta phases occurs gradually over depth ranges of several hundred meters, creating a complex landscape of nuclear matter configurations that determine the mechanical properties of the neutron star crust. The 2025 NICER observations provided the first direct measurements of crustal thickness and composition by analyzing the thermal emission from neutron star surfaces. These measurements revealed that neutron star crusts are typically 1–2 kilometers thick, representing only a tiny fraction of the neutron star's total radius. Despite this small thickness, the crust contains approximately 1% of the neutron star's total mass and plays a crucial role in determining the object's observable properties. The transition zone between the inner crust and the core represents one of the most dramatic phase transitions in nature. At densities around 200 million tons per cubic centimeter, atomic nuclei dissolve completely into a uniform fluid of neutrons, protons, and electrons. This transition, known as the neutron drip line, marks the boundary where individual nuclei can no longer exist as distinct entities. The nuclear pasta structures gradually give way to a superfluid of neutrons that can flow without friction or viscosity. The neutron star core exists in conditions impossible to recreate in any terrestrial laboratory. Densities in the core exceed those found in atomic nuclei by factors of 2 to 10, creating an environment where the normal rules of nuclear physics break down completely. The core material consists primarily of neutrons, but also contains significant populations of protons, electrons, and possibly exotic particles like hyperons, kaons, or delta particles that exist only under these extreme conditions. At the very center of the most massive neutron stars, matter might undergo an even more dramatic transformation into quark matter. In this state, the strong nuclear force that normally confines quarks within protons and neutrons becomes overwhelmed by the extreme density. Quarks exist as free particles in a soup of up, down, and strange quarks that behaves like a perfect fluid. Some theoretical models suggest that this quark matter might be absolutely stable, making it more tightly bound than any atomic nucleus. A 2025 study published in Physical Review Letters used lattice quantum chromodynamics to study neutron star interiors, obtaining new maximum bounds for the speed of sound inside these objects. The research provided better understanding of how pressure, temperature, and other properties relate to one another in the core. The properties of neutron stars are determined by quantum chromodynamics, the theory of the strong force that governs the interactions of protons and neutrons, quarks, and gluons. These internal structures directly influence the observable properties of neutron stars that astronomers have measured for decades. The relationship between mass and radius depends critically on the equation of state of neutron star matter, which is determined by the microscopic interactions between particles in the core. Stiffer equations of state, corresponding to matter that resists compression, allow neutron stars to reach larger radii for a given mass. Softer equations of state result in smaller, more compact neutron stars. The mechanical properties of the neutron star crust determine how these objects respond to external forces and internal stresses. The nuclear pasta structures can fracture during starquakes, leading to sudden changes in the neutron star's rotation rate and magnetic field configuration. The strength of the crust material determines the maximum stress that can build up before fracturing occurs, directly influencing the frequency and magnitude of starquake events. This hidden architecture beneath the neutron star surface represents a natural laboratory for studying matter under conditions that span the gap between atomic nuclei and black holes. The layered structure from crust to core encompasses density ranges that cover more than 6 orders of magnitude, each regime governed by different aspects of quantum mechanics, nuclear physics, and relativity. Yet for all this internal complexity, neutron stars reveal their secrets through one of the most remarkable phenomena in astrophysics: their ability to maintain perfect rotational stability while spinning at rates that would tear apart any ordinary object, spinning faster than helicopter blades. The rotational speeds achieved by these cosmic objects defy ordinary experience. The fastest confirmed pulsar, designated PSR J1748-248-2446 AD, completes 716 rotations every second. This means the surface of this neutron star moves at roughly 70,000 kilometers per second, or about 25% the speed of light. To put this in perspective, helicopter rotor blades typically spin at 300 to 400 revolutions per minute. This neutron star spins more than 100,000 times faster than the fastest helicopter blades while maintaining perfect stability across millions of years. The extreme rotation rates emerge from a fundamental law of physics called conservation of angular momentum. When the massive star's core collapses during the supernova explosion, it shrinks from a diameter of thousands of kilometers to just 20 kilometers across. Angular momentum must be conserved during this collapse, so as the core gets smaller, it spins faster. The process resembles a figure skater pulling in their arms to spin faster, except the neutron star undergoes a size reduction of more than 99% while accelerating to unimaginable speeds. The original star rotated slowly, completing one rotation every few days or weeks. During the core collapse, this leisurely rotation accelerates dramatically. If the original star had a rotation period of 30 days, the resulting neutron star would spin roughly 1,000 times per second after accounting for the size reduction. Additional factors like magnetic field interactions and mass loss during the supernova can modify this final spin rate, but conservation of angular momentum provides the basic mechanism that creates these cosmic speed demons. The 2025 radio telescope surveys discovered dozens of new millisecond pulsars with rotation periods shorter than previously thought possible. In 2025, AI pipelines cut analysis time of gravitational wave neutron star signals from hours to seconds. Advanced machine learning and detector upgrades doubled detection range, enabling more mergers to be seen per year. The Parkes Radio Telescope in Australia detected several pulsars spinning faster than 800 times per second, approaching theoretical limits for neutron star stability. These discoveries pushed the boundaries of what physicists believed possible for rotating neutron stars and provided new constraints on the equation of state of ultra-dense matter. These rapidly spinning neutron stars exist at the very edge of stability. The centrifugal force from rotation tries to tear the neutron star apart, while gravity holds it together. The balance between these forces determines the maximum possible spin rate for neutron stars. Theoretical calculations suggest that neutron stars cannot spin faster than about 1,500 rotations per second before centrifugal forces overcome gravitational attraction and rip the star apart. The breakup frequency depends critically on the neutron star's internal structure and composition. Stiffer equations of state, where matter resists compression more effectively, allow higher maximum spin rates. The constraint that the radius of PSRJ 1748-2446 AD is less than 13.2 kilometers for a solar mass object provides direct information about neutron star structure. This measurement technique uses the fact that neutron stars spinning at observed rates must be small enough that their surfaces remain gravitationally bound. The lighthouse effect creates the regular pulses that make neutron stars visible as pulsars. Charged particles accelerated along magnetic field lines emit beams of electromagnetic radiation that extend from the neutron star's magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. When the beams point toward Earth during each rotation, telescopes detect brief flashes of radio waves, X-rays, or gamma rays, with timing precision that rivals atomic clocks. The pulse timing reveals extraordinary detail about neutron star properties. Radio telescopes can measure pulse arrival times with accuracy better than 1 microsecond, allowing astronomers to track tiny changes in rotation rates over years or decades. These measurements provide information about the neutron star's moment of inertia, which depends on how mass is distributed within the star. Different internal structures produce different moments of inertia, making pulse timing a powerful probe of neutron star interiors. Long-term timing observations reveal that neutron stars gradually slow down as they age. The rotating magnetic field acts like a brake, carrying away rotational energy as electromagnetic radiation. Young neutron stars slow down rapidly, losing significant rotation speed over thousands of years. Older neutron stars reach equilibrium rotation rates where energy input from accretion balances magnetic braking, creating the population of millisecond pulsars observed today. Pulsar glitches represent one of the most dramatic phenomena in neutron star physics. These events involve sudden increases in rotation rate that occur without warning and can change the spin frequency by parts per million in fractions of a second. The 2025 monitoring campaigns detected over 200 new glitch events, providing unprecedented statistics on glitch properties and recovery timescales. Some glitches show permanent changes in rotation rate, while others exhibit complex recovery patterns that extend over months or years. The mechanism behind pulsar glitches involves the interaction between the neutron star's solid crust and its superfluid interior. The crust spins down gradually due to magnetic braking, while the superfluid core maintains higher rotation rates because it cannot couple directly to the magnetic field. When the difference between crust and core rotation rates becomes too large, the superfluid suddenly transfers angular momentum to the crust, causing the observed spin-up event. Pulsar timing arrays utilize networks of precisely timed pulsars to detect gravitational waves. The 2025 observations involves monitoring over 100 millisecond pulsars with timing precision approaching 10 nanoseconds. These cosmic timekeepers form a galaxy-sized gravitational wave detector that can sense the stretching and compression of space-time caused by supermassive black hole mergers occurring billions of light-years away. The correlated timing variations across multiple pulsars provide the signature of gravitational wave passage. The rotational energy stored in spinning neutron stars represents an enormous reservoir that powers various astronomical phenomena. A neutron star spinning 1,000 times per second contains rotational energy equivalent to the sun's total energy output over 30,000 years. This energy can power pulsar emission, accelerate relativistic jets, or drive electromagnetic phenomena in neutron star magnetospheres. The gradual release of rotational energy through magnetic braking provides a long-term power source that can operate for millions of years. These spinning cosmic lighthouses demonstrate that neutron stars operate as natural precision instruments that reveal fundamental physics operating under extreme conditions. Their rotation rates push matter to the limits of stability while providing cosmic laboratories for studying general relativity, nuclear physics, and the behavior of matter at densities exceeding atomic nuclei. Yet the most spectacular displays of neutron star physics occur not when these objects spin in isolation, but when cosmic circumstances bring them together in encounters that reshape the very fabric of space-time itself. When titans collide in cosmic violence, binary neutron star systems represent the ultimate cosmic time bombs, with two dense objects locked in an inexorable death spiral. These cosmic titans, each containing more mass than our sun compressed into a sphere smaller than Manhattan, have been orbiting for millions of years. The intense gravitational field of each neutron star distorts the shape of its companion, creating tidal bulges that slow their orbital motion. As they lose energy, they spiral inward with increasing speed, heading toward an inevitable collision that will reshape our understanding of the universe. The final seconds before impact unleash gravitational waves of unprecedented intensity. These ripples in spacetime carry away the orbital energy at an accelerating rate, causing the neutron stars to plunge toward each other faster and faster. The gravitational wave frequency increases from 35 Hz to over 1000 Hz in just 100 seconds, creating a cosmic chirp that sweeps through the sensitive band of LIGO-Virgo detectors. The amplitude of these waves grows exponentially as the separation distance shrinks from 300 kilometers to 0 in the last second before merger. In 2025, LIGO-Virgo recorded the first neutron star colliding with a mass gap object weighing 2.5 to 4.5 solar masses. The signal designated GW2305 solar masses. The signal designated GW2.529 marked a groundbreaking confirmation of mass gap binaries that challenged supernova models predicting such objects should be extremely rare. Advanced gravitational wave detectors achieved sensitivity improvements that allow detection of neutron star mergers out to distances exceeding 1 billion light-years. Each detection provided a three-dimensional view of space-time distortion as these massive objects twisted the fabric of reality around them. The moment of collision creates conditions more extreme than anything found elsewhere in the universe. When two neutron stars finally touch, their surfaces are moving at 100,000 kilometers per second, or one-third the speed of light. The impact generates temperatures exceeding 100 billion degrees Celsius, hot enough to break apart atomic nuclei and create a soup of free protons and neutrons. The collision site becomes a laboratory for nuclear physics operating at energy densities that dwarf the conditions inside atomic nuclei. The kilonova explosion that follows represents one of the most spectacular events in the cosmos. Within milliseconds of the merger, the disrupted neutron star material expands outward at speeds approaching 30,000 kilometers per second. This explosion creates a fireball that initially shines brighter than a billion suns, powered by the radioactive decay of freshly synthesized heavy elements. The kilonova can be detected across billions of light years, making it visible throughout most of the observable universe. The extreme conditions during neutron star mergers forge elements impossible to create through normal stellar processes. The collision ejects roughly 1/10 of a solar mass worth of neutron-rich material into space at high velocities. This material contains free neutrons with densities millions of times higher than found in ordinary matter. Within seconds of the merger, these neutrons get captured by atomic nuclei faster than they can decay, building up heavy elements through the rapid neutron capture process known as R-process nucleosynthesis. The 2025 discoveries confirmed that neutron star mergers serve as cosmic foundries for gold and platinum synthesis. Spectroscopic observations of kilonova light curves showed clear signatures of specific elements being formed and dispersed. Gold atoms created during the merger absorb and re-emit light at characteristic wavelengths that telescopes can detect for weeks after the initial explosion. The R process creates isotopes with neutron-to-proton ratios much higher than stable nuclei, forming a pathway to elements that cannot be produced through the slower neutron capture processes operating inside stars. The aftermath of neutron star mergers depends critically on the total mass of the colliding objects and their internal structure. Mergers involving two relatively low-mass neutron stars can produce a more massive neutron star that survives the collision. These remnant neutron stars inherit the combined angular momentum of the original binary system, often spinning hundreds of times per second. The intense magnetic fields from both original neutron stars get amplified and twisted during the merger, creating magnetic field configurations unlike anything seen in isolated neutron stars. More massive neutron star mergers cross the threshold where gravity overwhelms all other forces, creating stellar mass black holes surrounded by accretion disks of hot debris. The formation of these black holes occurs within milliseconds of the merger, as the combined mass exceeds the maximum possible mass for neutron star matter. The transition from neutron star to black hole represents one of the most dramatic phase changes in physics, where matter disappears behind an event horizon and becomes permanently isolated from the rest of the universe. The 2025 electromagnetic observations provided unprecedented views of the merger aftermath through multiple wavelengths of light. Gamma-ray telescopes detected short-duration gamma-ray bursts powered by relativistic jets launched from the merger site. These jets propagate at nearly the speed of light and create focused beams of high-energy radiation that can be seen across cosmological distances. Optical telescopes tracked the kilonova light curves as they evolved from blue to red over weeks, reflecting the changing composition of the expanding debris. The heavy elements created in neutron star mergers eventually become incorporated into future generations of stars and planets. Gold atoms forged in ancient neutron star collisions billions of years ago now exist in jewelry, electronics, and living organisms on Earth. The platinum in catalytic converters, the uranium in nuclear reactors, and the rare earth elements in smartphones all trace their origins to neutron star mergers that occurred throughout cosmic history. Each merger event enriches the surrounding space with heavy elements essential for planet formation and biological processes. These cosmic collisions demonstrate that the most violent events in the universe also serve as creative forces that build the chemical complexity necessary for life. The calcium in bones, the iron in blood, and the gold in wedding rings all originated in the violent collision of neutron stars that occurred long before our solar system formed. Yet beyond their role as cosmic alchemists, these mergers produce something even more remarkable. They create disturbances that propagate through the very foundation of reality itself. The fabric of space-time rings like a bell. When neutron stars collide, they generate gravitational waves that propagate outward at the speed of light, carrying encoded information about the collision across billions of light years. These ripples in space-time itself represent distortions in the geometry of space and time, stretching and compressing the universe as they travel. Einstein predicted these waves over a century ago, but detecting them required building the most sensitive instruments ever constructed. The LIGO and Virgo gravitational wave detectors sense distortions in spacetime so small they defy imagination. These instruments measure changes in distance that are 10,000 times smaller than the width of a proton. The detectors consist of laser interferometers with arms extending several kilometers in length. Laser light travels back and forth along these arms, and gravitational waves cause tiny changes in the arm lengths that show up as shifts in the laser interference patterns. The challenge lies in distinguishing genuine gravitational wave signals from the countless sources of noise that constantly shake the detectors. The 2025 upgrades to the LIGO-Virgo CAGRA network pushed gravitational wave sensitivity to unprecedented levels. Engineers reduced noise from Earth-based vibrations including earthquakes, traffic, and even ocean waves crashing on distant shores. They minimized vibrations from molecules in the optical coatings within the instruments and developed techniques to suppress quantum vacuum fluctuations that affect the laser beams. These improvements more than doubled the detection range for binary neutron star mergers from approximately 250 million light-years to about 550 million light-years, dramatically increasing the volume of space accessible to gravitational wave observations. Each gravitational wave detection provides a unique fingerprint of the colliding objects. The signal begins as a low-frequency chirp when the neutron stars orbit each other at large separations. As they spiral inward, the gravitational wave frequency increases from about 35 Hz to over 1000 Hz in the final seconds before merger. The rate of frequency increase depends on the total mass of the system, while the amplitude depends on the distance to the source. Tidal effects and frequency chirps reveal the stiffness of nuclear matter beyond lab densities. The 2025 discoveries about neutron star equations of state emerge from detailed analysis of gravitational wave signals. Tidal deformation occurs when the gravitational field of each neutron star distorts the shape of its companion, creating bulges that extract energy from the orbital motion. The magnitude of this deformation depends on how easily neutron star matter can be compressed or stretched, which is determined by the equation of state. Stiffer equations of state produce smaller tidal deformations, while softer equations allow larger deformations that show up as measurable changes in the gravitational wave phase evolution. These observations test Einstein's general relativity under conditions impossible to recreate in any laboratory, with gravitational wave waveform phase shifts from tidal deformability, providing a new equation of state constraints from GW7-817 in 2025 events. Neutron star mergers involve gravitational fields billions of times stronger than anything found in the solar system, with matter moving at significant fractions of light speed. The gravitational waves carry information about how space-time behaves in these extreme environments, allowing physicists to verify that general relativity remains valid even under the most extreme conditions nature can produce. The growing catalog of neutron star merger detections provides statistical power to constrain fundamental physics. The LIGO-Virgo CAGRA collaboration reached a significant milestone in 2025 by detecting its 200th gravitational wave candidate events during the ongoing fourth observing run. This catalog includes 2 or 3 binary neutron star mergers, 5 or 6 neutron star black hole mergers, and several events involving mass gap objects that exist between the heaviest neutron stars and lightest black holes. Each detection adds another data point for understanding the population properties of compact objects. Gravitational wave astronomy has opened an entirely new window on the universe that complements traditional electromagnetic observations. These waves travel through space without absorption or scattering, carrying pristine information about their sources across cosmological distances. Gravitational waves can penetrate dense matter that would block electromagnetic radiation, allowing observation of physical processes hidden from optical telescopes. The waves also encode information about the strong nuclear force operating inside neutron stars, providing insights impossible to obtain through particle physics experiments. The Dingo BNS algorithm developed in 2025 can fully characterize binary neutron star systems in about 1 second compared to about an hour for traditional methods, improving sky localization precision by 30% for rapid electromagnetic follow-up observations. Future gravitational wave detectors will reveal cosmic events occurring throughout the observable universe. Next-generation ground-based detectors will achieve sensitivities that allow detection of neutron star mergers at redshifts approaching 1, corresponding to look-back times of several billion years. Space-based detectors will access lower frequencies blocked by Earth-based noise, opening observation windows for massive black hole mergers and exotic compact objects. Third-generation detectors will measure gravitational wave polarizations and test alternative theories of gravity with unprecedented precision. The information carried by gravitational waves remains impossible to obtain through any other means. Electromagnetic radiation provides information about the surfaces and outer layers of astronomical objects, but gravitational waves encode the bulk properties of ultra-dense matter deep inside neutron stars. The waves carry signatures of phase transitions, exotic particle production, and the behavior of matter at densities exceeding atomic nuclei. These measurements can strain the equation of state of neutron star matter and test theories of quantum chromodynamics under extreme conditions. Gravitational wave observations have also revealed unexpected diversity in compact object masses and spins. The detection of neutron stars more massive than theoretical predictions suggested indicates that our understanding of nuclear matter remains incomplete. Some merger events produce remnants that exist in the gap between neutron stars and black holes, challenging traditional classification schemes. These discoveries demonstrate that gravitational wave astronomy continues to surprise scientists with phenomena that force revision of fundamental assumptions about stellar evolution and compact object formation. The precision of gravitational wave measurements approaches the theoretical limits imposed by quantum mechanics. Future improvements will focus on developing quantum-enhanced interferometry techniques that surpass the standard quantum limit. These advances will enable detection of individual neutron star oscillations, measurement of post-merger remnant properties, and observation of gravitational wave memory effects that permanently alter space-time geometry. Each gravitational wave detection reveals new aspects of laboratories for impossible physics. These cosmic objects push matter to extremes that dwarf anything we can achieve in the most advanced particle accelerators or high-pressure experiments. No lab can replicate nuclear density except heavy ion collisions at twice nuclear saturation density, but neutron stars exceed that by factors of 3 to 5, making them unique natural laboratories where physics operates under conditions impossible to recreate anywhere on Earth. The conditions inside neutron stars exceed the densities found in atomic nuclei by factors of 2 to 10, creating environments where the fundamental forces of nature behave in ways we are only beginning to understand. The extreme conditions within neutron stars challenge every aspect of our understanding of physics. Densities reach 500 million tons per cubic centimeter in neutron star cores, values so high that normal atoms cannot exist. At these densities, the electromagnetic force that keeps electrons in orbit around atomic nuclei becomes overwhelmed by gravitational and nuclear forces. Matter exists in states that have no earthly equivalent, where quantum mechanical effects dominate on macroscopic scales and the distinction between individual particles begins to break down. The 2025 observations from multiple space-based and ground-based telescopes provided unprecedented data about how matter behaves under these impossible conditions. X-ray timing observations revealed that neutron star matter responds to compression in ways that surprised theoretical physicists. The equation of state measurements showed that matter at nuclear densities and beyond exhibits properties that existing models had not predicted. These observations forced scientists to reconsider fundamental assumptions about how the strong nuclear force operates when protons and neutrons get packed together at extreme densities. A 2025 lattice quantum chromodynamics study revealed that the speed of sound in neutron star matter peaks above 1/3 the speed of light to approximately 0.75 times light speed at the highest densities. This result provides crucial constraints on how stiff neutron star matter becomes under extreme compression and helps explain how these objects can support masses exceeding 2.5 times that of our Sun. The speed of sound measurement represents a fundamental limit on how fast pressure waves can propagate through ultra-dense matter, directly constraining the equation of state that governs neutron star structure. Temperature conditions inside neutron stars create another frontier for impossible physics. Newly formed neutron stars have core temperatures exceeding 100 billion degrees Celsius, hot enough to break apart any atomic nucleus. Even after cooling for thousands of years, neutron star interiors maintain temperatures around 100 million degrees. These conditions allow physicists to study how matter behaves when thermal energy becomes comparable to nuclear binding energies, creating plasma states where nuclei dissociate and reform continuously. The interplay between quantum mechanics and general relativity reaches its most extreme expression inside neutron stars. Quantum degeneracy pressure from neutrons provides the primary support against gravitational collapse, demonstrating quantum effects operating on stellar scales. The uncertainty principle prevents neutrons from being localized to arbitrarily small volumes, creating a quantum mechanical pressure that can support objects containing more mass than our Sun. This represents one of the few places in the universe where quantum mechanics and general relativity must be solved simultaneously to understand the physics. Neutron stars probe the limits of how dense matter can become before collapsing into black holes. The maximum mass limit for neutron stars depends critically on the behavior of matter at densities exceeding that found in atomic nuclei. The 2025 gravitational wave detections revealed neutron stars with masses approaching 2.5 times the solar mass, indicating that matter at extreme densities must be stiffer than many theoretical models predicted. These measurements provide direct experimental constraints on quantum chromodynamics, the theory describing the strong nuclear force that holds atomic nuclei together. The study of neutron star matter has revealed exotic states that exist nowhere else in the observable universe. Deep within neutron star crusts, matter organizes itself into structures that physicists call nuclear pasta because of their resemblance to various pasta shapes. These formations represent some of the strongest materials ever discovered, with tensile strengths billions of times greater than steel. The nuclear pasta phases emerge when nuclear matter reaches densities where individual atomic nuclei begin to merge and reorganize into extended structures. At even higher densities in neutron star cores, matter might undergo phase transitions to states containing exotic particles, like hyperons, kaons, or deconfined quarks. These particles exist only under conditions of extreme density and pressure that cannot be sustained in any terrestrial laboratory. The presence of exotic matter would fundamentally alter how neutron stars behave, changing their cooling rates, magnetic field evolution, and maximum possible masses. The 2025 radius measurements from the NICER mission help distinguish between theoretical models containing exotic matter and those composed entirely of conventional nuclear particles. Neutron stars also serve as laboratories for studying the nuclear force under conditions of extreme isospin asymmetry. Normal atomic nuclei contain roughly equal numbers of protons and neutrons, but neutron star matter has neutron-to-proton ratios exceeding 20:1. This extreme neutron excess creates conditions where the nuclear force operates in regimes that cannot be studied through conventional nuclear physics experiments. The behavior of nuclear matter under these conditions determines crucial properties like neutron star cooling rates and the efficiency of various nuclear reactions. The precision timing of neutron star pulses allows scientists to test fundamental physics with accuracy exceeding that of atomic clocks. Pulsar timing measurements can detect changes in rotation rates smaller than 1 part in 10 to the power of 15, providing sensitivity to gravitational wave effects, orbital decay, and even the motion of our solar system through the galaxy. These measurements test general relativity and strong gravitational fields and provide unique laboratories for studying how gravity behaves when space-time curvature becomes significant. The 2025 discoveries revealed that neutron star observations are beginning to uncover physics beyond our current theories. Some neutron star properties cannot be explained using existing models of nuclear matter, suggesting that new physical processes operate under these extreme conditions. The detection of neutron stars more massive than theoretical predictions indicates that exotic matter states or new aspects of the strong nuclear force become important at the highest densities. These cosmic laboratories continue to surprise physicists with phenomena that require revisions to fundamental theories. The observation of star quakes that release more energy than the sun produces in centuries demonstrates mechanical properties of matter under conditions of extreme gravitational stress. The discovery of neutron stars with complex magnetic field geometries reveals plasma physics operating in regimes where magnetic pressure exceeds matter pressure by enormous factors. The ongoing revolution in observational capabilities promises to unlock even deeper mysteries hidden within these stellar remnants, as new technologies prepare to reveal secrets that have remained buried in the cosmos for billions of years. The future, written in neutron starlight. Advanced gravitational wave detectors and artificial intelligence pipelines now detect neutron star mergers across the cosmos, enabling multi-wavelength follow-ups within hours of detection. The LIGO-Virgo-CAGRA collaboration has implemented upgrades that more than double the detection range for binary neutron star mergers from approximately 250 million light-years to about 550 million light-years, while machine learning algorithms like DingoBNS can fully characterize merging neutron star systems in about 1 second compared to about an hour for traditional methods. Third-generation gravitational wave detectors will achieve sensitivity improvements of another factor of 10 beyond current instruments. The Einstein Telescope in Europe and Cosmic Explorer in the United States will observe neutron star mergers throughout most of the observable universe. These detectors will measure gravitational wave polarizations with unprecedented precision, testing alternative theories of gravity and revealing subtle effects that current instruments cannot detect. The improved sensitivity will allow detection of individual neutron star oscillations immediately after merger events, providing direct measurements of how these objects vibrate and ring down to equilibrium states. The Square Kilometer Array will add nanohertz gravitational wave detection through pulsar timing arrays, while the Laser Interferometer Space Antenna Space Interferometer will catch low-frequency signals blocked by Earth-based seismic noise. These complementary observation windows will reveal neutron star properties that no single detector type can access alone. Radio telescope arrays are preparing to discover thousands of new pulsars that will serve as cosmic laboratories for fundamental physics. The Square Kilometer Array will begin operations with sensitivity levels that exceed current radio telescopes by factors of 50. This instrument will detect millisecond pulsars throughout the Milky Way galaxy and in nearby galaxies, creating a comprehensive census of neutron star populations. The 500-meter aperture spherical telescope in China has already demonstrated capabilities for precise pulsar timing that will contribute to gravitational wave detection through pulsar timing arrays. These radio observations will reveal neutron star properties that gravitational waves cannot access. Pulsar timing measurements will determine neutron star moments of inertia with precision better than 1%, constraining internal structure models and equation of state parameters. The radio surveys will discover exotic pulsar systems, including neutron stars orbiting supermassive black holes, providing tests of general relativity in extreme gravitational fields. Some discoveries will reveal neutron stars with unusual magnetic field configurations or rotation properties that challenge current theoretical models. Advanced neural networks are learning to recognize subtle patterns in pulsar signals that human analysis might miss. These algorithms can detect timing variations caused by gravitational waves, identify glitch events, and measure neutron star mass and radius parameters from pulse profile analysis. Machine learning systems process data from multiple radio telescopes simultaneously, creating virtual instruments with effective collecting areas exceeding any single telescope. The artificial intelligence revolution in astronomy will discover rare neutron star phenomena that would otherwise remain hidden in vast datasets. The unsolved mysteries that future observations will address include fundamental questions about the nature of matter under extreme conditions. Current equation of state models disagree about whether neutron star cores contain exotic particles like hyperons or deconfined quarks. The improved gravitational wave sensitivity will detect post-merger remnants and measure their properties, revealing whether exotic matter phases exist at the highest densities. Radio observations will discover neutron stars with properties that current theories cannot explain, forcing revisions to models of stellar evolution and compact object formation. The detection of individual neutron star oscillations represents one of the most exciting frontiers in gravitational wave astronomy. These oscillations occur when neutron star mergers create remnant objects that vibrate at characteristic frequencies determined by their internal structure. The oscillation frequencies depend on the equation of state of neutron star matter, providing direct measurements of how matter behaves at nuclear densities and beyond. Future detectors will measure multiple oscillation modes simultaneously, revealing the internal stratification and composition of neutron star interiors. Neutron star studies will impact our understanding of the universe through connections to cosmology, nuclear physics, and fundamental interactions. Precise measurements of neutron star properties will constrain models of supernova explosions and stellar evolution, affecting calculations of chemical evolution in galaxies. The heavy elements produced in neutron star mergers seed future generations of stars and planets, making these cosmic collisions essential for understanding how complexity emerges in the universe. Neutron star equation of state measurements will inform models of proto-neutron stars formed during the first moments after supernova explosions. The quantum mechanical properties of neutron star matter will be probed through observations of superfluidity and superconductivity operating on stellar scales. Future timing observations will detect the coupling between neutron star crusts and superfluid interiors through glitch recovery patterns and rotational irregularities. These measurements will reveal how quantum effects scale up from atomic to macroscopic dimensions, providing insights into quantum mini-body physics that cannot be studied in terrestrial laboratories. The combination of improved gravitational wave detectors, advanced radio telescopes, space-based observatories, and artificial intelligence analysis will reveal neutron star properties with unprecedented precision. These observations will test fundamental theories including general relativity, quantum chromodynamics, and the standard model of particle physics under conditions impossible to recreate on Earth. The technological revolution underway promises to transform neutron stars from mysterious objects into cosmic laboratories that illuminate the deepest principles governing matter, energy, space, and time. Yet for all the technological advances and theoretical breakthroughs on the horizon, the neutron stars themselves continue to hold surprises that challenge our most fundamental assumptions about how the universe works. 3 groundbreaking discoveries in 2025 have fundamentally altered our understanding of neutron stars and their role in the cosmos. The detection of GW230529 revealed the first confirmed merger between a neutron star and a mass gap object, challenging stellar evolution models that predicted such encounters should be extremely rare. NICER's precise mass and radius measurements forced a revision of nuclear equations of state, showing that matter at extreme densities behaves differently than theoretical models predicted. Advanced artificial intelligence algorithms now analyze gravitational wave signals in seconds rather than hours, opening a new era in multi-messenger astronomy that enables rapid electromagnetic follow-up observations. These findings point toward even more revolutionary discoveries as third-generation gravitational wave detectors prepare to detect exotic phases in neutron star cores and reveal physics operating at the